Okay, so reactive power, Q. We measured in voltamps reactive. And let me go over a couple of examples. Q is going to be 0 when the load is resistive. What's the power factor for a resistive load? JT, what's the power factor for a resistive load? Remember, the power factor is just the cosine of theta V minus theta I, which is the same thing now. We can simplify that to cosine of theta S. Another way of asking it is, what's the difference in the angle between the voltage and the current through and across a resistive load? Is there any difference in the angle of the voltage and the current across a resistive load?
I'm not sure.
Okay, let's take a quick break and analyze that question. Let's say we've got here's a 3-volt source at 10 degrees, and it is across a resistive load. And the resistive load is, I don't know, maybe it's equal to 2 ohms. JT, tell me, what is the current that's flowing here?
It'd be 3 angle 10 divided by 2.
3 over 2 angle 10, right? So now tell me, for a resistive load, what is the difference in angle between the voltage and the current?
Can you repeat that one more time?
For a resistive load, what is the difference in angle between the voltage and the current?
Oh, 0.
0. And so therefore, what's the power factor going to be? Always
0.
So the power factor is the cosine of the difference in the angle.
Oh, it'd be 1.
So the cosine of 0, which is 1. So a resistive load will always have a power factor of 1. Let's do another one. For resistive load, there's no reactive power, and the power factor is 1. Stone, for a Q that's negative, and that's going to be true for any kind of capacitor, it'll have a negative reactive power. What's the power factor going to be?
Sir, I do not remember. I remember having this table up last class.
Yeah. Well, let's work it out. Let's work it out from first principles. 3 at an angle of 10. And now we're going to put it across a capacitor. And to make it easy, I'm going to say it's got a negative J impedance. You know it's going to be negative J something. Let's just make it negative J1. So now what is so Stone, tell me, what is our current going to be?
Wouldn't it just be divided by the impedance?
It's equal to V over Z, which is equal to 3 angle 10 over minus J, which is equal to 3 angle 10. What is negative J written in polar form?
Negative 90. 1 negative 90.
At a negative 90. So to divide them, we divide the magnitudes. And what do we do to the angles?
You add them, I think.
If you multiply, you'll add them. But since we're going to divide these guys, you'll subtract. But since you're subtracting a negative, it's like adding.
Positive.
So you get 100 degrees. And now my same question that I asked to JT is to you. What is the difference in angle between the voltage and the current?
It'd be positive 90. Well, actually, voltage is going to be
relative to the voltage.
100.
Relative to the voltage, what's happening to the current? Because voltage is more important. So we always measure the current relative to the voltage. So relative to this voltage, what's the angle of the current?
The angle's going up by 90.
It's going to be 90 degrees up. And so it's going to be, the power factor is going to be, what's cosine of 90?
0.
0, because it's going to be leading by 90 degrees. And then the last combination here is if we have a inductive load. And Jesse, doing the same kind of reasoning that we just did for the capacitive load, what will the power factor be?
It'll also be 0.
That's right. But instead of leading by 90, it will be,
Lagging by 90.
that's it. Now, most real world loads are not going to be purely resistive, purely capacitive, or purely inductive. Instead, they're going to be somewhere between a resistive and capacitive, or resistive and inductive load. And if that's the case, if it's kind of, I'll just do the one example of sort of RL-ish. If it's a resistor in series with an inductor, then it's still going to take our Q from here. We will still have a positive reactive power component. And now the power factor is going to be somewhere between 0 and 1. But because it's inductive, it will be lagging by some amount. And that's the way that I've drawn it up here. In this region, in every region in this quadrant, this is a lagging because our Q is positive, and every region down here that we would draw would be leading. So every region up here, it's like an RL load, and every region down here, it would be an RC node. Every region up here, your current angle is lagging behind your voltage. Every region down here, your current angle is leading in front of your voltage angle. What I'm telling you is that whenever you get a problem dealing with power, you want to start off by drawing this power triangle right here. That should be your first step. How are you going to get to that power triangle? By using one of these rules down here to draw it. You'll have enough information. Like, for instance, let's just work it out using this particular example. You were given this voltage. It's across some sort of load. You can figure out what the current is through the load just by Ohm's law. Now you've got V of t and you've got I of t. So you can get your VRMS and your IRMS. You can put it right in here, multiply them together. You've got your complex power phasor. You draw that complex power phasor, and now you can find out what the real part of the power is. You can find out what the average power is. It's the real part of your power phasor. You can find out what the apparent power is. It's the magnitude of the power phasor. You can find out what the reactive power is. It's the imaginary part of the power phasor.